Okay, so hi everyone. Last lecture we discussed the FRI protocol, and now we're going to delve into the analysis of the protocol and see how it works and prove the correctness, completeness, and soundness and all of that. And also see some beautiful type of mathematical problems regarding distances between subspaces, which I like a lot. So let's start by recapping what we did yesterday. So first of all, we had a problem that we tried to solve, and the problem was that can we take the Reed-Solomon code, the set of all univariate polynomials of low degree, and can we get a good test for it? And by that I mean, suppose that I'm getting a function f, and I can make queries to that function, to the truth table of this function. Can I make a small number of queries to the function, maybe like O of 1? And if it is a low degree polynomial, I would say yes. And if it is far from being low degree, then I will say no. And we kind of mentioned that this problem is impossible to do using O of 1 queries. It's a very hard problem. And so we considered a stronger model. And the stronger model, I kind of want to, I don't think I can zoom here. Oh, yeah, I can't. Okay, so just to say that in this model, we have a prover and a verifier. And I want to make sure that all of the points are like extremely clear. So we have the function f. This is the function that we want to test. So think about this function as some long vector which represents the evaluation of the function f over its domain L. So it literally is the value of f at 0, the value of f at 1, the value of f at 2. We have a prover that can read the entire description, the entire truth table. And we have a verifier which can only query it, only probe it locally at a very small number of places. So that's, so far, if we have just the verifier in F, then that's the property testing model that we've been doing all along. But now we also have a prover, which kind of like give us a proof, and we can communicate with him. And each time the prover can send some very long proof that we will not read entirely, but rather only make small number of queries, right? And what I'm trying to do now is to tie this abstract model to the actual protocol that we saw yesterday and kind of like make sure that we exactly see what happens. But at least the notion of this model of IOPs, you should think about having a function, that you can query, and then you have a prover which sends you some more functions that you can query. That's the idea. Okay.
I have a question.
Yes.
So before Reed-Solomon code, when we looked at linearity testing and low degree testing, we described our function as mapping from some field or some tuple of field to a field element. But here we introduce this additional L parameter. Why is that the case?
Yes. So that's a very good question. So first of all, everything that we did, we chose to evaluate the polynomials over the entire field. But we could have done, we can also we could have chosen to restrict it to a smaller domain. It's completely up to our discretion. But now you might say, so why do I suddenly bother about it? And the reason why I suddenly bother about it is because we want to have a protocol where we each time will fold the domain. And so what will happen is that we will evaluate the polynomials on smaller and smaller and smaller domain. And so by getting this notational flexibility, by extending the definition to also include evaluation of those subsets of the field, this just allows us to save a lot of notation, and we just have these rather than defining lots of different problems, different Reed-Solomons for different sizes, we just have now a parameter and we can just recurse on that. So that's the main idea.
But is it the case that f is not defined over the entire field? Is it only defined over L?
I mean, f. So this is where we should be careful. So we have f, the formal polynomial. That's just a formal polynomial, and you can evaluate it wherever you'd like on any field that you'd like. But when we are writing down the truth table, it means that we have this vector of evaluations. And the vector of evaluations would be exactly corresponding to each point in L. So you cannot query, you cannot make a query to F, which is in a point which is outside of L. Does this make sense?
Okay, yes, thanks.
Good. Okay, so we try to devise a protocol, and we did it in 2-3 steps maybe. So the first step was to kind of say, well, there is a nice trick that we have from fast Fourier transform, where you can take a function and break it down into an odd function and an even function, where the variable, instead, like if you started with the variable which is f to some element, then you can evaluate the even and odd polynomials in the element squared. So in some sense, what happens is we kind of contract the domain into 2. And the way to think about it, like think if we want to evaluate something, over L, which is -3, 2, -3, -2, -1, 0, 1, 2, and 3. So the moment that we square everything, then the domain folded. We don't have, the minuses. Okay, so what we're doing is we say, fine, we can have a pooler, and the pooler will take the function f. He will break it into 2 different sub-functions, g and h, and then, send these 2 functions, and we'll try to first check for consistency. We'll send that the 2 functions that the prover sent really are consistent with the function that we can query. And then we just recurse on the whole thing. So even to begin, before I go to the next step, just to say exactly what's happened here. So I have the function, which is a function that I want to test. This is exactly as the function here that we have, in the sky, which the prover knows and the verifier tries to test. We only care, this is our input, and we care about that. So that's f. And then the prover is sending, these g and h, and these are these 2 messages, 2 PCPs, 2 big functions that are being sent, and we don't read these entire functions everywhere, but rather we just query here, for example, just in these 3 places. Okay, so the next step that we had, so we said that here we have a problem. We actually had 2 problems. So the first problem was that if we do this thing, then we recurse and we split the problem into 2, but then we solve both of these problems. And so we get nothing by this recursion. We don't get any saving, and the complexity is large. So we get linear number of queries. And we also saw that there could be this situation that distance decays per iteration, because there could be these cancellations. Maybe, we had a polynomial, and it was a quadratic polynomial, and we, the moment that we split it into, even and odd polynomials, somehow the coefficient of x squared got canceled, and we lost degree. Okay. And then to fix that, we added this idea of folding, of random folding. So what we said is that, we'll have the prover taking, as before, the function f, breaking it into the odd and even parts, sending them. So again, this would be these messages. The verifier would then reply with just some random field element. So that would be a message from the verifier. And then the prover, as opposed to, it would just take these 2 functions, do this random linear combination of them, and send it back to the verifier. And then the verifier would check consistency on this part, and then continue to recurse on that. So the gist of that is that instead of breaking into odd and even, and then checking both odd and even, we break into odd and even, then we combine odd and even randomly to get only 1 function, and we then continue to iterate regarding on this function. So this means that the recursion makes the size of the input smaller by a factor of half at each time. And then after log rounds, we will converging and we get the desired query complexity. And finally, we can state where we left off last time, which is the actual FRI protocol. So just to mention, the previous protocol that I mentioned works, but we can actually make it even more efficient. And the way that we did that was to consider these nice correlated queries, and also to eliminate like sending explicitly the functions that we then fold. So what is the actual protocol? So we start with this function f, this f in the sky, that we want to test. This would be our f0, the first function. And notice that the prover knows this function entirely, and the verifier doesn't. It only gets the parameters, field size, this subdomain L and T. And what's going on is the following thing. The verifier chooses some random field elements, and then it sends one field element. The prover in turn takes the two functions, breaks them into odd and even, and then fold them, with the coefficient alpha 0, and then send the folded function. And then the verifier, sends another random coin. The prover folds again and sends the folded function again. And this repeats for r rounds until finally the prover is sending the last tiny function. This is function that like the domain was exponentially contracted, so it's like something of constant size. And once we sent the last function, the verifier stops interacting with the prover. So the first step, the interaction part, is over. And now what we do, the verifier does this consistency checks. So what does it mean? We take this, random point in L, and we check whether the condition of the folding, which we show this is exactly how the folding looks like, whether it holds for mu squared, like whether this folding was done correctly. And then we take the same element and we check whether it holds for mu to the fourth, and so on and so forth. And maybe notice here that the function f is defined over L. So, we think about a variable x, and f1 is defined over L squared. So we always think about the variable being, x squared. So when we are evaluating here, we only want to evaluate it on like elements of the field which are squared. So it's all kind of nice and consistent. And the last function will, so what we're doing is we're checking this consistency. And the way of thinking about it is that we care about f0, but after the first round of the protocol, similarly as we had in the GKR protocol that you saw yesterday, and after the first round, this reduces the problem into checking low degree of a different problem, f1. And then we do again, and then reduce the problem to f2 and until we get into fr. And then finally we get the last function, which we can read entirely and just check whether it's low degree, and then the recursion takes care. So this is the entire protocol. And before we get into anything, regarding the analysis, now would be a fantastic point to ask any questions you might have regarding the definitions, regarding the model, regarding the protocol. So if anything is unclear at all, please do let me know.
So this last point that the last function is low degree, this requires still a check, right? It's very easy for the verifier to do that check because the degree is very small, and it would amount to just looking at the truth table of this small function and figuring
exactly.
it out. Right.
So think about, maybe like a nice way of thinking about it is, we start with this like massive function. Okay, it looks like just a rectangle, but this is a massive rectangle. And then we kind of like break this rectangle into two rectangles of half the size, and we then merge them into one, which is like half the size. And then we do it half the size and half the size. And at the end of the day, we like can actually have a an input which consists of just two elements. And we can break these two elements into, 1 and 1, and then choose a single element. So what happened? I mean, you don't really go that deep into the recursion, but you can definitely stop, and the function is of constant size, and then you can, just like read the entire truth table of the function and just check for yourself.
Right.
Because not only the degree is getting smaller, also the domain. The domain becomes tiny. It could be just a few elements. Exactly this L that we have discussed. Yeah, but thank you. That's a fantastic question.
One last thing is, the only thing now that I don't understand, I couldn't understand from the last lecture is the diagrams in the previous slide. So you have these diagrams that show how errors can be introduced.
Yes.
Like you see at the bottom, you have this G and H that could have errors in various places, and then this would lead to double the rate of error that G and H have in F, right?
Yeah.
And the reason for this is that G can affect two indices. Every entry of G can affect two entries of F. Is that true? Is that the reason?
That's exactly the point. So I mean, the intuition is like you can do it like the intuition that we had with the Fourier, the first Fourier transform. So you have a function, and because the variable is squared, then the values in 3 and -3, like they would kind of like merge to be the same. So what is happening? So when you take this function G, and you think about what is happening, so you have a smaller function, which is just the over a smaller domain. That's like, let's say, the even part. And because the even part is contracted by a factor of 2, then it means that it must affect 2 points in the larger place, right? Because like we are taking n over 2 points and n over 2 points, and we use both of them to interpolate regarding the entire domain. And you'll see later with the equation, maybe it's a good place to put it here. Then let me see. Okay. Then here is exactly where you can see how the functions are contributing. So what is happening is that when you look at the next function, the F1 function, then you look at the even and odd contributions, and both of them are contributing. So one time they would contribute the value both of u and the value of minus u. Both of them contribute to the value of u squared. So in fact, it is the average. So for example, the cancellation is exactly if f0 of m is 1 and f0 of minus, not m, of minus mu is -1, then this term becomes 0. And this is exactly how we could get like distance which would drop. Like there could be cancellation. So suppose that the correct word was like just the all 0 string, and then an error is -1 and 1. So when you kind of average over them, yeah.
I see. So this cancellation is only in the case where we assume that F0's table was all 0. So for anything else, like just
yeah, but you'll see that this is actually this is something that we do a lot in coding theory. Well, the only code word which really matters is the all 0 code word. And why is that? If the code is linear, because this is a linear subspace, so you can always rotate and shift linearly. So in some sense, by arguments of symmetry, and we'll see it later in the lecture, like even the analysis, you kind of like say you can always assume without loss of generality that we're dealing with the all 0 code word. And so because like even if it's a different code word, it would still be shifts, would just not 0 out, but rather become equal to the original code word. But we'll do it more formally.
Yes.
So I'm just checking the chat. Let me see. Okay.
I had a question.
Yes.
Yeah, so can you give us some intuition of how this relates to the code word? So I don't have good intuition of how this test relates to the notion of a code word. So like when you define the function f mapping from L to F,
I mean,
what is the message space? What is the code word space over there?
yeah, sure. So just when we say the Reed-Solomon code, then you kind of like think about, you take some values, let's say, 1, 7, 8, 1. That's your message. And now what you want to do is you want to encode it. And how do you encode it? You take a univariate polynomial that at 0 takes the value 1, and then takes the value 7, then takes the value 8, and then takes the value 1. And you evaluate this polynomial, and then you give you give the evaluation of this polynomial, which is of degree 3, which takes these values, and you evaluate it over the entire domain L. And that's the way you take a message, and which is like just 4 numbers, and you actually can extend it to however large L that you'd like, millions and millions of numbers that would be uniquely determined by that.
I see. So the message space is not specified in this function f, right?
So the message space is not specified. It is implicitly specified by the degree. But it is true. Yes, we think about the code as the collection of all code words, as opposed to there are 2 perspectives that one can think about the code. One of them would be to say, it's a mapping that takes X and map it in the code word C of X. And the other perspective would be take the linear subspace, which consists of all C of X's for some X. So we take the second, the latter approach, which is the standard one, I think, in the coding theoretic literature.
Got it. Thanks.
Okay. So we do have time constraints. So if you have more questions, there are quite a bit in the chat. So maybe we have time for one more question if you want to unmute yourself.
So one question I had, what happens when we go all the way down the recursion? You said we should not go all the way down the recursion, but
yeah, so the point is that we aim to get this constant query complexity. So all we want to do is to get to the point where the domain is small enough, so it's some arbitrary constant, and then we can just read the whole thing. So that's,
yeah, but I was thinking if we go down all the way, the truth table will become exactly of size 1, and then we'll be checking whether that point is of degree 1, which will always be true. So what am I missing?
I mean, one has to be exactly, this is exactly why you need to be careful with the conditions of the field and how small it could get. I think you can go down until 2 points. We'll see at when we do the analysis that the recursion has to terminate at a certain condition before things become degenerate. But it's just some complete degeneration of
okay.
Okay.
Maybe just a small remark, because regarding the notation, there are 2 things which are a bit confusing maybe. So you're using the round brackets, which looks like an evaluation of a function, but it's not. It's just a lookup. So this confused me a lot. So maybe it would be maybe better to use square brackets on the verifier side, so to indicate really that he doesn't evaluate, he just looks what's written in the table.
So
and this also
regarding
every time when the verifier accesses some f on position mu or wherever, he doesn't evaluate, so he just makes a lookup.
Okay, I'm not sure I see I'm not sure I see what you're saying. So maybe you can point it out when does it appear on the slide?
Yeah. So what was confusing for me is that on the verifier of the side, we rewrite f0 evaluated at mu. You know, so this looks like we're having a polynomial here, and we evaluate it at mu. But in fact, we don't. Yeah, we just make a lookup, and this also explains why mu can only come from the can be only be picked from the domain L.
I see.
Because I asked this last time. Yeah. And the second thing of notation, which might be a bit confusing, is that you write L square, which could mean L times L. But what you mean is that you halve the number of points.
Thank you for saying this thing. I think, so what we're doing here is that there is always a trade-off between like not being ambiguous and not making the notation too cumbersome. This is some approximation of it. It's important to say this explicitly what we mean by L squared, because we're not tensoring or anything, so we're all in consensus. And regarding this point of evaluation, the way I kind of view it is maybe the missing point is that we should say that verifier queries all of these points, and then he holds these values, and we can do them. So whenever we write that the verifier do this thing, it actually does make a query and gets this value of f, and then it holds it, and do the computation. Okay, so because of time constraints, we'll have to move on, but I'll stay after the lecture if there are more questions. Okay, so we said that we were doing that, and we have this query pattern, and the whole thing can be repeated t times, so we can boost the soundness if we'd like. Okay, now we have this monster of a theorem, which is actually quite simple. It just looks long. So first of all, the main corollary of that is just like saying that we get this soundness L, which is roughly O of L over F. So it means that if we choose the field to be large enough, we can make it as small as we'd like. And and also that we are bounded by some constants here. So it's again consistent with what we saw with low degree testing and stuff like that. Now, the reason why the full theorem in its full generality look as intimidating is because we're decoupling the random alphas that we send for the folding and the mu, which is done for the consistency checks. So in some sense, the inner probability refers to the probability of success with respect to the queries that we make, and the outer probability refers to the interaction that we have with the prover. So kind of like to say, we have this probability of success in the queries, and this probability will actually hold only if the interaction was good enough. So this is why we get this. So it's it's a long expression, but it's just like this captures the essence of it. Okay. So we need to start with some notation and to make everything precise and clear. So let's see what we have. So we'll have our domains, and because I don't want to write L to the powers, and so we just have this Li, which corresponds to the size of the domain in the iteration. So it would just like get smaller and smaller and smaller. And then we'll have Di, which is a degree, and the degree also like drops and drops by a factor of 2. So Di would be the degree of the polynomial in the ith round. And similarly, remember that we evaluate at mu, and then at mu squared, and then at mu to the 4th. So we do the same thing. And instead of like writing that, mu I would be the point that we evaluate in round I. Okay, so just like definition, nothing, just notation. And notice that the rate of the code, sorry for that, okay. So notice that the rate of the code, and what is the rate of the code in this case? It's the amount of information which is captured by the degree versus the size of the domain in which we evaluate. So this always remain constant. because we start with D and then we look at D over 2 degree, but also domain of size L over 2. So it just remains constant, and we'll denote this constant by rho for rate. Okay. So next, we'll have the relative distance between any two code words, and that's a property of the Reed-Solomon code. It just, the relative distance is 1 minus rho. So somehow what's special about the Reed-Solomon code word that satisfies that the distance, the relative distance plus rate is equal 1. So if you know it from coding theory, then good, but other than that, take it as a well-known fact regarding the Reed-Solomon code. Okay, so, let's fix the function f0. This is the function that we want to test. This is the goal, to check whether f0 is of low degree or not. And we fix some malicious proval strategy, which we'll denote by f squiggly line, by p tilde. And notice something important in the protocol, that what is the prover allowed to do? The prover gets, some random element from the verifier, and then it needs to send some function f, like FRI at each one of the rounds. So in fact, if the prover does anything else except sending functions, we can always say, well, you're not following the protocol, so we don't listen to you. And so we can say without loss of generality that the prover can be fully specified by the functions that it would send in each round. And notice that this function depends on the random choices, alpha 0 to alpha I to alpha I, which are the random elements that the verifier send, which specify how to fold. Okay, so we do that, and okay. Now there is an important definition to make. It looks long, but it's actually a simple thing. We call it the failure set. And what is the failure set? It's exactly what it is. It's the set of points on which the test will fail, in which we'll detect and say that we can reject. So more formally, for each one of the rounds, we'll define the failure set in round I to be all elements of the domain in the ith round, such that if I take the function, which is purportedly the fold, and I evaluate it at the point A, and then I look at the fold and evaluate at the point A, then I won't get the same value. So this is exactly the consistency checks that the verifier is doing. So for each one of the round, I'm saying what are the bad points that if I kind of catch it, I know that the prover cheated. Okay. So we have this, and then we have another slightly confusing definition, but we'll do it slowly, and then hopefully it wouldn't be. So we'll define this notion of coset distance. So what would be a coset distance? So we call that the whole protocol, the whole folding. What we're doing is we kind of capitalize on this symmetry of minus and plus. And so, we keep thinking as in FFTs, again, regarding these symmetric points, x and minus x. So we want to have a distance where we kind of say that something that G and H differs on a point if either x or minus x disagree. So it might be the case that one of them, that they would agree on the positive term, but if they don't agree on the negative term, on one of the term, we'll still count it as distance. And why we do that? We do that because we will then folding them. So if there was error in one of the sides, in the minus or the plus, then it would, because we're bundling it randomly, then it would kind of still count as an error. We'll still get an error this way. So that's the coset distance. And why it's called coset, you'll see later. Okay, and we're going to keep track of distances for each one of the rounds. So what do I mean by that? So I'll just have this notation of delta I, which tells me what is the distance of the function that I'm looking at the ith round, which is FI, from the Reed-Solomon code. Right? So this is like our distance at each one of the iteration. Okay, bear with me. That's the last. It is a long definition slide, but we won't have any more slides like that. So this is something that I can anticipate a confusion. So let me be really explicit about what. In this lecture, when we will use f hat, we will use f hat in a slightly different way than before. We will use f hat as the closest polynomial, low degree polynomial, to f. So for example, if you give me some function f, which is sufficiently close, which is close to a unique low degree polynomial, then by f hat, I will refer to the correction of this noisy function into a low degree polynomial, right? So f could be a noisy version of f hat, and maybe the coding theoretic perspective is, you can maybe think about all of these things being valid polynomials, and suppose that I'm getting some, so these are, this would be like a f hat, and then I might get a point which is closest uniquely to only one point, and that would be my f. And the point is that when I'm adding the hat, that would be correcting to the valid code. I don't know if it's helpful, but yeah. Okay. And the last important definition that we'll have is that of the error set. And the error set is pretty much like fail that we had before. The fail refers to when the protocol will fail, and the error set, on the other hand, let me highlight it, tells us in what places we have noise, right? So this is exactly, if we go here, it will tell us at what locations the polynomial does not agree with its, like the function does not agrees with its polynomial correction. Does not agree with the closest polynomial there. And notice that this is also in coset distance. So it suffices it doesn't agree on the positive or on the negative part, and we still count that as a distance. Okay, so notice that if the distance is, so if like the distance at iteration y, if delta I, distance at iteration 1, I, is less than 1 minus 4 over 2, which is like half the distance of the code. This is called the unique decoding radius of the Reed-Solomon code. So essentially all this means is that if delta I is smaller than the unique decoding radius, then there is only one low degree polynomial to which we are closest, and this is, in this case, it makes sense to write this f hat. If the distance in the iteration is greater than that, then we might be, equally close to two different code words, and then this is ill-defined. So we'll only use this f hat when we are within the unique decoding radius. Okay, so that was a long definitional slide. Any questions regarding these definitions before we get to the actual content?
I have a question. So you said that the rate is same in each round's code, and what is that symbol? Is
And
it
what's
true?
the what?
The rate is same in each round's code, right? In the second line. And you said rate plus distance equals 1, relative distance equals 1. So why do you have two different symbols over there? For rate and...
So okay, thank you for that. So what I meant here is that the Reed-Solomon code word has this property that the rate plus the relative distance of Reed-Solomon is equal to 1. But what does it mean, the relative distance of Reed-Solomon? It means that each two low degree polynomials would disagree on this fraction of the domain. But the distance of reads of the code is very different from the distance of the arbitrary function that the verifier, that the prover sent. So like there is, the distance of the code, this is one thing. And then completely independent of that, the prover is sending some functions. And these functions might be really far from a log-degree polynomial. They might be exactly a log-degree polynomial. So this kind of like defines that. Does this answer what you asked?
Yes. So this delta is the distance of the function from the code word, and the relative distance is distance between two valid code words.
Exactly.
Okay.
I mean, the distance of the code is like fixed, and
Right.
we have a relative distance for each one of the rounds, which just refers to the distance between FI and the code of this particular function FI from the Reed-Solomon code. And by the way, I should say I'm experimenting here with a dubious notation. So the coset distance, it's a triangle which is kind of like colored by yellow. So this is not just like highlighting, it's actually a notation, a colorful notation. So I'll give reminders while I'm doing it, but triangle without, that is not colored, it's just regular distance, and the coset distance would be, this yellow triangle. Okay, so let's get into the more interesting part, which is distortion. So what is distortion? That's one of my favorite parts in the FRI protocol. And, we intuitively argued that this random folding should preserve distance with high probability, right? So we had this exact confusing diagram where we kind of said, well, I have this function, and this point contributes 2 points, so I have distance here, and I have distance here, and then when I'm merging it, I get the distance from this place and the distance from this place. That's what's happened intuitively. But actually, there is something, a beautiful mathematical phenomenon which is going on here. So let's kind of formalize exactly what we mean by that and how one can achieve it. So, good. So, take some function f and some distance delta. So I want to say what is the drop set of f with respect to parameter delta. So before we look at the equation, let's say what it intuitively means. It just tells us what are the points, what are the random coefficients according to which we fold where we will lose distance, right? So think about it. I started here with distance, let's say 10% and 10%, and then I'm merging it. So I started with 20%, and then I'm merging it, and I have 20%. So I want to say, what are the alphas, the collection of all alphas, such that when I'm doing this folding, when I go from here to here, I lose distance. So the distance drops. So that would be the drop set. Okay? And notice this is being done with respect to the regular pointwise distance. I just look at all points such that folding f with respect to alpha, the distance from Reed-Solomon drops from what we had before. Okay, so that's the drop set. And we then have the following theorem. And the theorem tells us that, take any function that you'd like and define delta to be the distance of this function from the Reed-Solomon code world, before this Reed-Solomon code. And then we have this delta star, which is just some constant. Don't really worry about the exact definition. So what we know is that if the distance is at most 1 minus rho over 2, if we are in the unique decoding radius, if there exists a single, if the function itself is close to some low degree, some unique low degree polynomial, then the probability that we will be of an element being in the drop set is bounded by L over F. So think about, I don't know, L as being, think about F being 1 million L. So it's a probability of 1 over a million of getting this kind of thing. So this tells us that within the unique decoding radius, only a very small fraction of the random elements alphas according to which we fold would lead us to lose distance. And the second part of this statement would say, well, if we are outside of the unique decoding radius, then we won't be able to do what we had before. So, but we will be able to do it with respect to some general constant. So this means the following thing. So if the prover sent us a function, and this function is close to a low degree polynomial, so we can use the structure of low degree polynomials and the correction and stuff like that to argue about preserving that distance. But if the prover is sending us something which is completely non-related and it's like just randomly chosen values which are very, very far from having any structure at all, then we won't be able to control the drop set absolutely with respect to that distance, but rather we'll have some constant which is good enough for us. But either way, the takeaway message from this theorem tells us that, like, in regardless of the distance of the function from the code, we will always be able to reject with constant. The distance will always be able to preserve constant distance. So we might not be the exact distance that we started with, but it will always be some constant distance. Okay.
This drop set is a good thing or a bad thing? Like,
No, that's a great question. So the drop set is a bad set. It's kind of like it's the set of bad verifier messages. So remember that what's happening, the prover is sending a function, f, and then the verifier sends alpha, and the prover folds according to alpha. So we want to preserve the distance. We want to say that if we started with a function which is far from low degree, we'll be able to catch it. So we want that in each round, our goal is to maintain the distance. And the drop set is exactly the places where the verifier chose something bad randomness that led him to lose distance. So as long as we don't hit the drop set, everything is good. Okay, so to say,
I have a question.
Yes.
So the drop set is parameterized by the function f and the delta, but in the description of this set, there is nowhere delta is not appearing anywhere inside the set.
Sorry, can you say that again?
So the drop set is parameterized by this function f and delta parameter, but inside the set, there is no occurrence of delta.
Ew.
It is d, right? Oh, is it delta? Okay.
Yeah, so what I'm saying is that, like, I want to say what the drop set of f of delta is. What elements would make f lose in its folding a value of delta. So I say, what are all of the elements such that after I folded, my distance from Rip Solomon is most delta.
Oh, okay. I misread that as d instead of delta. Sorry.
Oh yeah. We should also do, self-correction to handwriting. Okay, thank you. So just to say, what's happening in the FRI protocol, we want to ask what is the probability that we'll get some distortion. So what does it mean that we'll have distortion? It means that there exists, some round in which we hit the drop set. Right? So now I want to kind of like say, what is the probability that nowhere in the entire protocol did the distance drop? So we started with distance 20% and it maintained until the end. So I want to say the bad situation where distortion happened, where we dropped distance, is if there exists a round where we chose a random element such that the folding would lead to a drop. So what is that? That is, we just take a union bound, so we sum over all of the rounds, and in each round the probability is exactly L over F. But L is like Li because the size of L depends on the round in which we are. And to write it more explicitly, the dependency is, like Li is just, if we define it to be L divided by 2 to the I. So nothing really happens here. And so the entire probability that distortion happened is this, 2L over F. So as long as F is, 1,000,000 times larger, then this will happen with just a tiny probability, and we don't have to worry at all. So yeah, so this is what it said, and what we want to do is kind of like say the following thing. For now, let's assume that there is no distortion at all, that like we never hit this like bad event, which happens with a tiny probability that there is distortion. And then we can kind of say, suppose that the distance always remain the same in all of the iterations, like it's always like at least this absolute constant. Let's try to analyze what is the probability that we reject. So we can kind of forget at all about this, what happens if we lose distance. Okay, any questions regarding that?
So in the theorem, delta is to do with the blockwise distance, and then the drop set's to do with the non-colored in distance.
Yes, this is, yes. And
does that mean that you can still like iterate down?
I mean, the only reason why we're talking about the blockwise, because we are referring to like to the folding, right? So what happens is that we need to count the distance with respect to the correct object. So it is really confusing. I mean, I think you'll see that maybe in the next slide it will become a bit more clear, but yeah, and we'll try to keep together, also try to see if I'm not coloring, well, this one is correct here, yeah. So, yeah, so we're going to see this quite explicitly, why exactly we use the coset distance, because we want to keep track. Whenever we'll do folding, we refer to element which is folded, we'll use the coset distance. Okay, so I want to show you the analysis, and let's do as much as we can, get as much like understanding that we can, and I think that the way to see the analysis, there are two steps. We can kind of look at the most interesting case, like the most natural prover strategy, and then we can also, so we'll start by saying, suppose that we have a prover which behaves reasonably. What is reasonably we'll see in a way, but like, at least to me, the prover behaves in the way that, like in the natural way that one would want to cheat. And we'll show how we deal with that case. And then we have another case where we can be saying, well, if it does something completely different, then we'll also be able to catch that. So let me just say what I mean. So we're starting with this prover, which adapts a consistent strategy, but noisy one. So what does it mean? Like the idea of this prover would be, we start with some function, which is of not of low degree, but we're trying to convince that it is of large degree. So what we'll do is we'll kind of like add a little bit of noise in a gradual way and try to build more and more and more noise, such that eventually through the rounds and the folding, this would become a function of low degree. Okay, so in some sense, this is the prover which doesn't do any drastic jump. It doesn't like completely change the polynomial. It doesn't do crazy things. So what does it mean more formally? We'll assume two conditions. The first condition is that all the functions that the prover will send would be within unique decoding radius. So all of them would be, slightly corrupted polynomials, but it wouldn't send something which is complete, junk, which doesn't resemble a polynomial at all. And the second part would be that all of them, so the moment that all of the polynomials are, within unique decoding, then we have these correction polynomials, these f hats. So we can kind of like say, well, let's look at all of the functions the prover sent and look at all of their corrections. So these corrections are actually folding off each other, right? So that's the idea. So this is a prover which try to cheat by noise, by adding noise. Now, later we'll show that if one of these conditions is broken, like for example, if you send me a function which is like extremely far from low degree, then we can catch that. or if you have this like function which is not a folding, then in the consistency check we will find it. So in some sense, to me, this is like the interesting case, or the subtle one.
One question. So
Yes.
shouldn't the functions that are inside the fold be without hat?
The function where without hat?
Inside the fold operation. The functions that you put inside the fold operation, they should be without the hat, right?
No, because like what we'll do is like in this mental experiment, we're kind of like saying we have these polynomials. These polynomials are all uniquely closed, and now we're like trying to ignore the noise entirely and just check whether the actual low degree polynomials are folding of each other. This is what we are assuming here. You'll see later how we deal with the case if that doesn't hold.
Okay.
But what I do really say here that everything is within unique decoding radius. So correct the functions in the analysis in our head and forget about the other ones in a sense. So let's like do it, and I think it will become much clearer. So I want to show you that in this case, the probability that we will reject would be the amount, like the relative distance at the first of the function at the beginning. So we have this function delta, and remember we discussed this error, which is again in this coset structure. These are all of the alphas in which the function does not agree with its correction. These are all of the noisy points. Right? So in some sense, maybe a good picture to have in mind is that we might have these functions FIs, and then somebody is just like putting a little bit of noise here, a little bit of noise here, and a little bit of noise here. Okay, right? And so error, the erroring set would be all of these points which where the function doesn't agree with its correction, but it's done in this coset structure. So it's like it's enough that if it happens with x or with minus x. Okay, so how do we prove this thing? So first of all, we do the important trick that we'll do all the time, which is kind of like rotate the space and assume without loss of generality that the self-correction of the polynomial is 0. So this doesn't change anything, but it makes our life really easy. Why does it make our life really easy? So we know now that the function, the original function that we want to test, it's actually like f is actually the all 0 string. It's like the function which is like valued 0 all over the place, but it's not, but like, delta percent of it was corrupted. So it's like 0 everywhere except for some places where it takes some other values. Okay. But it does much more than that, actually, because now we know that when we fold the 0 code word, it would still be 0. And so like all of the prover messages, like all the self-correction that of everything that the prover sends, it's just 0, 0, 0, 0, 0. So each round, the prover just like take, zeros and change a delta fraction of them. So things become much clearer in our head, and it's easier to see things. Now, also, the last message that the prover is sending is a message that we're actually, like the last function is a function that we are reading entirely. So if we're reading it entirely, then it better be the all 0, because we're checking that it's a low degree polynomial. So, so the last message itself is completely just the 0 string, the 0 function. Okay, so in that case, let's say that we, chose this element on which we do the consistency test, which is actually in the error set. Now, notice that this is like the best that we can expect, right? I mean, we choose the error at random, and we want to succeed with probability, error, the size of error, the fraction of error from all points. So if the random guess is not in error, then we can't do anything. And we also don't need to, because of this is what we're trying to prove. So we choose a point which in which there was actually a corruption, And now we're doing a trick which is really simple, but again, helpful. What we do is the following thing. Like, we know that there is some error in the beginning, and we know that there is no error in the end, right? Because like we started, well, in the soundless case, we're getting a function which is delta far from being low degree, and at the end we just got the all zero strings, which we know is of low degree. So what happens is that there has to be some point where we switched from a corrupted point to a non-corrupted point. And let's denote the largest, like the further in the round where we still have an error before the prover changes strategy, right? Because like by kind of like an intermediate value theorem type of statement, there has to exist a point where, you know, we got from noisy to non-noisy, from corruption to no corruption. So we fix that point. Now the more
one question.
Yes.
So here you have written that fixing mu0 also determines mu1 to mu_r. Why is that the case?
That fixing mu0 also, where did I write this?
Determines mu1 to mu_r.
Oh yeah. Yes, of course. Because we said that the query pattern is we query mu0 and then mu0 squared and then mu0 to the fourth.
Okay, right.
In some sense, it determines everything. Thank you. Okay, so now notice that like the point where we still have errors, it can't be the last one, because this is the one which we fully read and we know that there are no errors. So, you know, we have this like latest where there is still error, and this is a number between 0 to r-1. And now, you know, what can we say? By the maximality of J, we know that everything after J must be, you know, completely kosher. Everything has to be according to the prescription, because there is no error at all. So we know that mu J plus 1 is outside of the error set. And what does that tell us? It tells us that like at this point, the function and the correction must agree. And you know, we just get a 0. And so we'll make the following claim, which we'll show, you know, using in 5 minutes in the next slide, and then we're essentially done. So what we will show is that in this case, if we fold the function and look, on the other hand, look at like folding the correction of the function, then they must disagree. And the point here is that if this is happening, this is exactly the constraint that we are checking. This is exactly the test that the verifier is doing. This is how we designed it. So all we have to show that in this particular case, we will reject. So in some sense, this part of the proof, what we essentially did is we kind of like said, well, if the prover is behaving in this reasonable way, then it means that it spreads some noise, and at some point he has to stop spreading the noise. So let's zoom in on that point and show that on the one round where we go from noise to noise, not noise, we will catch the prover. That's the idea. Any questions regarding that?
So is J the round number where we are going from non-noisy, I guess, noisy to non-noisy, or is it the other way around?
Is what? Sorry.
So is J the index where we are going from a noisy function to a non-noisy function?
Yeah, J is the maximum index while we are still, like while the point is still in the error set. It's still, you know, where you have a disagreement, when you have this noise.
Okay.
Okay. Okay, so let's just, you know, we reduce the problem into just proving this claim here. So let's do that. And the proof follows by 3 easy steps. So the first step is just a small observation. We say, suppose that we have an element, and that element is not in the error set. And remember, we still have the definition of the error set here. It means that this is just, you know, a point where actually both of the minus and the plus cases, the function agrees on A. So it's an A, well, the function agrees with the self-correction. In this case, it would mean that it would be equal to 0 because the self-correction is a 0 polynomial. So what do we have here? We look at the fold according to this alpha at the point alpha squared. This is just a definition. We know that here the function is equal to the correction. And then essentially all we know is that the fold of the function is the same as fold of the correction, right? Because it takes the same values. So this is how we designed it. Okay, but what does this tell us? It tells us that like the fold of the function and the fold of the corrected function can differ in at most half the size of the error set, right? Because like if it's not in the error set, they agree. Otherwise, they can disagree. But can anyone tell me why there is a factor of half? Yes, so as Tal is writing in the comments, so it's because of the squaring that we're doing, because of the error could come from here or from here, and so we have this factor of half. But that's the only thing. Now, this implies that the operation of polynomial correction and folding, this operation commute. What does it mean? That if you fold the function and then correct, it's exactly the same as first correcting, then fold. And why is that? It's because they differ in at most, this like a delta fraction of the location, which means that they are inside the unique decoding radius. So in some sense, we are always staying within the range from the 0 code word, and so we can always go back to that. Okay, so now we have essentially like 3 more lines here. And what's happening here is the following. So we say, suppose that now we do have some element which is in the error set. So it means that either they disagree like on the positive term, or on the either they disagree on A or on minus A. So suppose that this alpha J, that this element random folding, alpha J is how we like the random element that we do, F plus alpha J, G plus alpha J H. So suppose that this alpha J still leads to the folding being equal at this point, right? I mean, suppose that by some way we have an element which leads to an error, but somehow by seemingly magic, the folding would still agree. And we'll argue that this is impossible. And why is that impossible? Because the distance of the folded function from the code, well, that's exactly the distance of the folded function from its correction. Why? Because definitionally, I mean, we are in the unique decoding radius. So the distance from the code is the distance from the closest code word, which is that. And we know that folding and correcting commute. So instead of fold and correct, we can correct and fold. And then we know that the distance must be less than delta, right? Because it means that there exists a point where we actually don't get an error. So the distance is no longer as it was before delta, but rather we at least lost 1 point here where we had correction. But now something is wrong, right? Because we can't lose distance, because we said that distance is like losing distance is exactly having a distortion, which we prove that, I mean, we didn't prove, but rather we said this is the case where the analysis showed that there is no distortion. And this means, and this is the last point here, that we assume that we have some mu element in the error set. And if it's not in the drop set, and we know that it is not in the drop set, which means that this cannot happen, and thus it means that the folding of the function and the folding of this correction must disagree on that point. And so it's a bit of a convoluted argument, right? Like in some way, we're trying to show that that the fold will disagree, and we show that the only way in which the fold of the function and the correction will somehow agree is if we drop least distance, and this is exactly why we do the folding in the random way, which prevents dropping. Okay, so that's regarding the analysis of the noisy case. And I don't think I'll have enough time to do the other case fully, so let me just, very quickly tell you the high-level idea of what is happening there, and we can use the rest of the time to like give more intuition and answer the question. So what is the other case? The other case is that the prover is behaving drastically. What do I mean by that? Either the prover jumps to like something which is very, very, very far from having a nice structure, or it goes to some perfectly valid low-degree functions, but ones which are inconsistent. What do you mean by that? One of the two cases. So this is exactly, by the way, the negation of the condition that we had before. So before we had two conditions that must hold, and now we have one condition or the other condition. So either there exists at least one function which is very far from the code, so which is outside of the unique decoding. It's like, suppose it's like, think about it as if the code word is 0, then it means that it's something like some string which is mostly doesn't have any zeros at all in it. Like it's like really, really, really corrupted. And intuitively, this makes things easier for us because we now have something which is like really corrupted, so we can probe it less. And the other case is that maybe, the functions are perfectly closed and everything is perfectly good, but at some point, there exists a round where we take a function and the folding, the function that we send is not at all the folding of the previous function. So in kind of sense, we started with the all 0 code word and then we moved to the all 1 code word. So both of them are a distance, both of them are low degree, both of them, are whatever we want, but like it's just not the same thing. And intuitively here, if this is the case, if we switch the function, because this is a code and each two low degree polynomials differ on many points, then also this would be something that is easy to catch. Okay, so that's the idea. And the lemma that we'll show in this case is, that the probability that we will reject is precisely the minimum between that and the distance of the code.